Testing 1, 2, 3. Right. Good morning. Today we go to chapter 10. Completely different things. In this chapter, we study about sequence and series. Right. So this part is in Gauss algebra, and then pre-calculus. Now we go back to that. Now we study this again, but this time we put some calculus on it. We study from the calculus perspective. Right. Let me write out the definition. Right, slightly different definition. In here, we define that as a list of numbers instead of a function of positive numbers. A sequence, we denote by the curly bracket, which means it's just like a list. Remember, when we use the calculator to use the list, we put that in the curly bracket. Which is a list of numbers. of the form so we have the list of numbers, and that is called a sequence. A sequence may be generated by a recursion recurrence relation. All right, and the recurrent relation, we have a function of this term is a function of the previous term. In this case, the first term is given. So we know the first term, and then this formula gives us the second term, and the second term gives the third term, and so on. We can also define with an explicit formula. In which case we say this term is a function of n. So there's nothing new here. By the way, each AI is called a term. So we call each one is a term in the sequence. Right, there's nothing new here. We define this in Gaussian algebra and pre-calculus. Right. Let's look at the first example. The question is, write the first four terms and the recurrent relation. So we are given this, and this one is a function of n. So there's no n and an plus 1 in here. So this formula, this is called an explicit formula. Right. Now, So in that case, we just choose n to be the first 4 terms. So let's choose n equal to 1 to 4. N equal to 1. Now it's just like a function where we put in the numbers for this n. We're going to put the number for that n. This should be 1. And that's just 1/2. And then we choose n to be 2. A2 will be 1 over 2 square, 1/4. N equal to 3. A3, 1 over 2 cubed, 1/8. N equal to 4. A4, 1 over 2 to the 4th power, 1 over 16. So in that case, the sequence an is equal to, now just write down the terms. 1/2, 1/4, 1/8, 1 over 16, and so on. So that's just a set of numbers, right? Now we will determine the recurrent relation. So in order to get to the next term, from this term, what do we have to do? So 1/2, and then half of that, and then half of that. So pretty much we just multiply by 1/2 to get from this term to the next, and so on. So in this case, the recurrent relation is this. We have either we write an or an plus 1. Let's say an plus 1 equal to a sub n. So to get to the next term from this term, we multiply 1/2 into it, and then we know that the first term is equal to 1/2. As always, we need to have the first term in the recursion relation. So we can go from this term, the first term, to the second, and then from the second to the third, and so on. By the way, we can enter the sequence using the calculator. So hit mode, in the function parametric, polar, and sequence, obviously we choose the last one for sequence. So hit mode and choose sequence. Right. Second mode quick. Right. Now we hit y equal to, and then we just enter the sequence. So we could enter the sequence like 1. I'll use the fraction 2. Alpha y equal to 1 over 2 to the n power. Right? And then we see the sequence of numbers. Second graph, sorry. So 1/2, 1/4, and then so on. Right. Now, we can also enter the recursion relation in here. Notice that second graph, we have this list of numbers, right? Now, if we want to enter as the recursion relation instead. So we go to the second one. This is for U, the sequence U. This is the sequence V. We're going to enter 1/2 we can enter like that. Or if we shift the index, we can also say, how about we can say an equal to 1/2 an minus 1. That also works, right? So this term is the previous term times 1/2. However, when we do this, the first term is still 1/2. Or we say these formulas work for n greater than or equal to 1. Right. So this is the recursion relation. Either that or this, it doesn't matter. It's just this term with the previous one. We can write n plus 1 and n, or n and n minus 1, either way. But on the calculator, here we're going to enter is 1/2 and then V, this is the V, so we have to a little V, so here alpha, not alpha, sorry, second V, open parentheses of n minus 1. So this button is nice. We have X for function, T for parametrics, theta for polar, and N for sequence. So when we hit this button, it gives us whatever the mode the calculator is on. So this term is 1/2 of the previous term. That's how we enter it. And then we determine the first term to be 1/2. There's a problem with it. We see. Right. Actually, it's fine. As you see, both sequences are the same. So here we have the recursion, the explicit formula, and this is the recursion formula. And we start with n equal to 1. And we define in recursion relation, we have to determine the first term. Right. Two. Write the first 4 terms and the explicit formula. So we have the recurrence relation an plus 1 equal to an minus 3. And the first term is 5. Oh, sorry. Once again, thank you. Yes. So hit mode and have to choose the sequence mode. So highlight the sequence and hit enter. And then second mode. And then we can hit y equal to, and that gives us the calculator in the sequence mode. Right. So this we have the recursion relation. Let me clear out the calculator. Clear this. And clear. And clear. So everything's clear. Yes. So to get to the sequence, if it is in the sequence mode, y equal 2, and then we can enter this. Actually, if we enter this in the calculator, it has to be like this. I'm just saying. So the first term is 1. I'm sorry. This should be n. So we start with n equal to 1. The sequence for this term is equal to the previous term minus 3. And then we start with the first term equal to 5. Right, so we're going to enter. So we enter this into the calculator for this recursion relation. So U, V, and W is on 7, 8, and 9, but we have to hit the second button, and then 7. So that's U. So this term is equal to the previous one, n minus 1 minus 3. And the first term is 5. Either we hit graph to get the sequence, which is a straight line now, or second table, write out the first 4 terms. And then we say the first term is equal to 5. Right. Of course, if we have the calculator like that, or we do this by hand. For the second term, we're going to put 2 and 2 in here. So we have n equal to 2. And we put, n equal to 1. Put 1 in here. 1 plus 1 is 2. And n is equal to a1 minus 3. Right? So the recursion relation is this. Put 1 in for n. 1 plus 1 is 2. And a1 minus 3. So a1 is 5. 5 minus 3 is 2. Now let n equal to 2. We put 2 in here. 2 plus 1 is 3. And 2 in here. And then we take 2 minus 3. Never mind, this is correct. It's negative 1. And then we take n equal to 3. Put 3 in here. We have the fourth term is a3 minus 3. Put 3 in here, a3 minus 3. So we have minus 1 minus 3 is minus 4. So in this sequence, the first 4 terms, 5, 2, negative 1, negative 4, and so on. In course algebra and with calculus, we call this is arithmetic sequence. So what we do is, from this term to the next, we keep subtract 2. Subtract 3, sorry. To get from this term to the next. But all of that, how do we turn this into an explicit formula? Right. Which means we have to write this an as a function of n. So there's no an minus 1 or anything like this, the n term is given by the function of n. So the way we look at this is we start with 5. And we keep subtracting. For the first term is 5. The second term we subtract 3. Should be like this, sorry. The first term is 5, so we start with 5, which is good. And then the second term we subtract 2. The third term we subtract 2 times -3. The third term, there are 3 of them. So think about this. I will spell it out. First term is 5. The second term 5 minus 3. The third term, to get to 5, we're going to subtract 3 2 times. And to get to the fourth term, subtract 3 2 and 3 times. So if this pattern continue, when we get to the end term, we start with 5 and we subtract 3 how many times? So the second need 1, third 2, fourth 3. So it's always we take n minus 1 times -3 from 5. So the explicit formula is 5 minus 3 times n minus 1. And this is an explicit formula for it. Right. Next. So we could have a recursion relation, and then we write the explicit formulas, or we have explicit formula, we write the recursion formula. To make sure that those two are the same, we can always hit y equal to, and this time go to v. And for the explicit formula, we just say 5 minus 3 times n minus 1. And hit second table, we should have the same, we should have identical sequence, which is good. Right. Next, now we have some calculus with it, meaning derivative and integral, but mostly derivative. Right. I'm not going to write everything. I'm just going to write this. If the terms of the sequence h of n approach a unique number L as n increases. Right. And by this we mean an can be made arbitrarily close to L by checking n sufficiently large. And then we say Now just, that is the definition of limit, by the way. So we just say limit of a sub n at n goes to infinity equal to L. And we say that limit as this. And the sequence converges to L. Right, so converges meaning that the limit approach to that number. Of course, the converge and diverge, we did define this back in section 8.9 in terms of improper integral. Converges pretty much, it converges to a number, and diverges when it does not. Right. If the terms do not approach a single number, or should say a unique number, the sequence has no limit. Or we say the sequence diverges. Right. So in a sense, if there's a limit, converges. If there's no limit, diverges. Now we look at the first example. Write the first 4 terms. And discuss the limit. Right, let's clear this. Clear everything. And we enter this sequence. Right? So, alpha y equal to, that is the fraction kind of small, sorry, -1 to the n power divided by n squared plus 1. Right. And it don't hit graph. Don't see much. We good, right? Yeah, sometimes I have the face cam so I can tell if it is moving. Right, so it's good. Right, so y equal to, and we enter the sequence there, which is good. Now, graph, we have a bunch of decimal places, so kind of have to. If it would be nice if we turn this into a fraction, so that's fine. Now I'm not sure if it works. How about alpha and trace? We don't have the function, so there's no option here. Hit the variable y variables. Do we have the sequence? No. So, oh, by the way, it's a lot easier than we see. So y equal to, this is the sequence u, right? So all we need to do is second u, open parentheses, that gives us the first term. Again, second, number 7, that gives us the second terms. Now if we want the whole list, just second u, and then we want the first 4 terms, second, parentheses, 1, 2, 3, and 4. Close that, close the parentheses, and then we have the sequence. Let's change this to fraction. So it's very easy to do. First 4 terms, negative 1/2, 1/5, negative 1/10, 1/17, and then so on. Right. Yeah. Either we put that with the bracket or not. It's not really important. Or we just give them a list. It's fine, right? So, and then if this continue, look like getting smaller and smaller. I mean, I should say that. I should not say that. What I should say is the magnitude, if we don't have the negative sign, by the way, because of negative 1 to the n power, this will alternate between positive and negative. That's the first thing. Second, if we just ignore the negative sign, the magnitudes, the numbers get smaller and smaller. So it looks like this approaching to 0. That sequence says. Right. Now, how do we actually write the limit? We just say limit of this one. So rather using the function, now we write this for a sequence. When n go to infinity, this will go to 0. Right. And how do we can say that mathematically? Well, I think that in the next section we actually learn about the limit of the sequence, which is not which is no different than the limit for a function. Right now we just see the parent and guess the number pretty much. 2. We have this sequence, cosine of n pi, n equal to 1 to infinity. Right, so that's easy. Just once again put 1, 2, 3, 4, and the question wants us the first 4 terms, so we're going to list the first 4 terms. So we can enter that in U, or just keep that for a moment. Just go to V doesn't matter. The sequence V. Right. Cosine of n times pi. Right. Just make sure that it is in the radian mode. Here, radian. So it's good. Second quick. And we have just that. Right. Hit graph. In particular, second graph to get the table. And in this sequence we have -1 for the first term, because cosine of pi is -1, and cosine of 2 pi or cosine of 0 is 1, cosine of 3 pi -1 and 1, and then alternating like that. So rather than writing -1 to the n power, we can also write that, which alternating the signs as well. Now, if it's switching between -1 and 1, the limit does not exist because it does not approach into a number. Or we say limit cosine of n pi at n go to infinity does not exist. Or we say the sequence diverges. Or we say the sequence is divergent. Right. How about we have a recurrence relation. Right. So again, let's write the first 4 terms. So n equal to, we know an is equal to 1. When we let n equal to 1, if we put 1 in here, we have a2 equal to -2 times a1, will give us -2 times 1, -2. N equal to 2. Put 2 in here. We have a3 equal to -2 a2. So -2 times -1, -2 times -2 is 4. And n equal to 3. Put 3 in here. a4 -2 a3 right. So again, if we use the calculator, I'm going to clear this. I'm going to write this term is equal to the previous term times -2. -2 times the previous terms, right? And the first term is 1. Right. Second table. So we say an equal to 1, -2, 4, -8, and so on. And if this pattern continue, we will go to infinity. Or we say when n go to infinity, a sub n equal to infinity. In this case, we still say the sequence diverges or is divergent. So we have three cases. If the limit goes to a number, then we say the limit is convergent, or we should say it, or the sequence converges to 1. Converges to 0, sorry. Right. So if the limit exists equal to a number, then the sequence converges to that number. If the limit does not exist, then it is divergent or diverges. Or even though if the limit exists, I mean infinity is not really a number. So if the limit is infinity, then we also say the sequence is divergent or the sequence diverges. Right. So if there's a limit, if there's a number, it is convergent, otherwise divergent. C. Find the limit for the sequence now. The nice thing is about sequence, not really nice, but when we say find the limit of the sequence, we assume that n goes to infinity. We don't even need to say as n goes to infinity. Now, if the sequence is 4n cubed over n cubed plus 1, so we just find the limit of 4n cubed over n cubed plus 1 as n goes to infinity. Right, so to find the limit of a sequence is just like the limit of a function. In this case, we have two polynomials here. So this is a very useful thing. We said as n goes to infinity, actually could be positive or negative infinity. Only the highest power terms matters. So in this case, when we say about limit of this one, since n goes to infinity, infinity cubed plus 1, infinity plus 1 is still infinity. So we're just going to drop the 1 because infinity plus 1 is still infinity. So we just take the highest power, the n cubed. So in that case, we have the limit at n goes to infinity of 4n cubed over n cubed. N cubed and n cubed cancel out. We just have the limit as n go to infinity of 4, which is equal to 4. Now if we have the graph like we have on this side, this graph, at n goes to infinity, the sequence go to 4. Right, so simple enough. Next, we have infinite series. sorry. We only have one, so that should be 2. Infinite series. A. Definition. By the way, the infinite series, the series always win an S. But sometimes it is. We use that as a singular form, but with an S. Now given a set of numbers, or we mean a sequence, we have the list of numbers. The sum, we're going to write like this: A1 plus A2 plus, I should say an index. And obviously, this is an infinite series if this one go indefinitely. Yeah. So as you see, we use this in the singular form, but still with an S. Now, we will define a partial sum . Associated to this series is right. So a sequence is a list of numbers or just individual terms. Now this is the sum. S sub 1, we have just the first term. S sub 2, the sum of the first 2 terms. S sub 3, the sum of the first 3 terms. And you have the idea. I mean, I should not put a dot there. Sorry. Very misleading. A dot here. So in that case, when we go to the S sub n, this is the sum of the first n terms. So a sequence is individual terms. A series is a sum from the first term to that particular term. Right. And then we say if the sequence of partial sum S of n has a limit then we say the series converges. To that limit. And we write the sum of ak from k equal to 1 to infinity is the limit as as n goes to infinity of S of n, or the limit of the partial sums of ak is equal to L. If this sequence of partial sums diverges, then the series diverges. And the series diverges. Right. So we have a sequence and then an infinite series. By the way, by default, when we say a series, we mean that infinite series already. So by default, we say a series, we mean an infinite series. Right. And so a series is a sum and a sequence is a particular term. Right. And let's take 5-minute break. We continue at 9:07. Test 2 will go from 8.4 to 10.4. Right. Actually, that's what I'm about to bring up. I'll switch back in just a minute. So if I go to YouTube and go to my channel, and of course we are live right now. So it's good. Oops, I never meant to go there. Anyway, so of course we have the list, the playlist for the class that I'm teaching. Of course, is Calculus 2 right now, and of course those are all the videos that we have up to this point, 11 days, and also the test 1 review and the test 2 review. For some weird reason, on the home page of my web page, and the end of the playlist is just up to this point. But if you click on the playlist, it actually have everything on it, up to the review. And once we have this video, I always, when I end the stream, I put that at the end. So just go to the playlist and then I should have everything. Right. 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 Now we're back to this. And I think the link on eCampus should go to the playlist directly. Right. Have the first example here. So consider the infinite series. For the partial sum, we have s sub n. For the infinite series, we just have s without the subscript. We don't write s sub infinity, we just write s. So what is 1/2 plus 1/4 plus 1/8 indefinitely? Right. So there are a lot of ways to visualize this, and if we have the graph over here, so we have 1/2, and after that we have a half of a half, and then a half of a half of a half, and then we just keep adding to it. So bottom line is, instead of doing like this, think about it this way. Let's see, I'm trying to draw a bow and arrow here, a recurve bow. So let's say we shoot an arrow here. It goes from here to the target. And first, it will travel half a distance, and after that, it travel a half of the remaining distance, and half of the remaining distance. And if we just add all of this up, essentially it will go to 1. So that's easy. By this reasoning, right? Shoot an arrow to a target. At first it travels half the distance, and then half of the remaining distance, and then half the remaining distance. By the way, somebody says that, Zeno or the ancient Greek philosopher, they said that this one will not add up to infinity. Will not add up to 1, because doesn't matter how small the number is, we can always cut that in half. So in a sense, the arrow cannot hit the target, because doesn't matter how close it is from an arrow to a target, doesn't matter how small the distance is, you can always cut that in half. But of course we know that is not true. If we add this indefinitely, it is equal to 1. And essentially the difference between the arrow hitting the target or not is the difference between the infinity or not infinity. Right. So instead of using the square like this, I'm using this visualization. Or if we want to write out as in terms of the summation. Right. So the summation of 1/2 to the k power, because essentially we have 1/2 to the k power, like 1/2 to the first, 1/2 to the second, 1/2 to the third, and so on. Add all of them up, we have 1. Right. Second example. Consider the infinite series. S 0.9 plus 0.09 0.009. First, find the partial sum. S1, S2, and S3. Oh, yeah. Either you write like this, or you can also write like 1/2 to the k power is equal to 1 to the k power. So the power goes to the top, the power goes to the bottom. 1 to the k power, just 1. Yeah. So either we have 1/2 to the k power or 1/2 to the k power. They're all equivalent. Yeah, we can write like this, or we can write like that. Sorry. Yeah, the reason I write like this, so it just emphasizes the fact that we multiply 1/2 every time. Right. Now back to this. The partial sum. The first sum of S1 is just the first term, just 0.9. S2, the sum of the first two terms, A1 plus A2. S3, sum of the first three terms. Right, so that's easy. Now if this continue, what will be the values of the infinite sum? Of course, we only do that if it exists. Of course, if this continue, we have 0.9999, and of course that go to infinity. I mean, if it go indefinitely, it goes to 1. Sorry, that's all obvious, right? Or we say the series is convergent. Or we say the series converges. To 1. Right. The next problem is a little long. So I'll go to the next page. Right. Kind of interesting though. Consider the infinite series. I'll find the first 4 terms of the sequence of the partial sums. Right. For the first 4 terms of the sequence, of partial sum. Right. Now, this will be a little more complicated. So the first term is just A1. So when we write like this, we mean the n term in the sequence is 1 over k sum k plus 1. So for a sub 1, we're going to put 1 in for k. K is 1, 1 plus 1, 1 half. Now, the second, a sub 2, sorry, I'm thinking ahead. First term and plus second term equal to, right, S2, sum of the first two terms, A1 plus A2. So I'm going to put 1 in for K. And 2 in for K. One half. And 2 and 3, so plus 1, 6. One half plus 1, 6. 2/3. Sum of the first three terms, A1, A2, A3. The first term, put 1 in for K. 1 and 1 plus 1. K is equal to 2, 2, 2 plus 1. K equal to 3, 3, 3 plus 1. So 1 half, 1 6, 3 and 4, 1 12. That 3/4. And then S4 is A1 plus A2 plus A3 plus A4. I'm not going to write all the terms because that we already have the first three terms is S3. So I'm going to write this as the recursion relation. S3 plus A4, right? We just add a new term to it. S3 is 3/4. A4 is where we put 4 in for K. So 3/4, which is what we have here, plus 1 over 20, which is 4/5. Now, isn't this nice? By nice, I mean 1 over 2, 2 over 3, 3 over 4, 4 over 5, 5 over 6, and then so on. Now, if this continue, what do you think the sums will be? Right. Now, if this pattern continue, even though we have the sum of a bunch of fractions, but if this pattern continue, we go to S and keep doing this, and we end up with what? As you see, first 1/2, second 2/3, 3 3/4, fourth 4/5, n over n plus 1. And if this is the case, the limit as n goes to infinity, or the limit of n over n plus 1 at n goes to infinity now, just like what we did earlier, take the highest power terms and the bottoms, take n. So only the highest power terms matters. N over n is 1. The limit of 1 is 1. So this also goes to 1. So essentially the last 3 examples, all of those series goes to 1, and it's all kind of different series. It goes to 1 at different rate. Right, now this we need to write this, let's say number 3. Derive the formula for so what we did here is we do a bunch of examples and we come up with the pattern, but that's not a proof. We see that if this pattern continue, indeed we have that, but again this is not a proof. So how do we prove this? Right, now we have a sub n is equal to 1 k times k plus 1. Now, way back in section 8.5, when we have something like this, it can be partial fraction decomposed, right? So we can decompose this into partial fraction. And if we do that, sorry, just need to be consistent here. The subscript is k. Sorry, keep doing that. Yeah, but the s is n. This one is n is correct, but the subscript for each sequence is k. Right. So we write ak. Now I don't want to. It is very easy to do partial fraction of this, but if you do, we end up with 1 of k plus 1. Subtract 1 to k. So if we do the partial fraction, we have that. I'm not gonna write everything. Now back to the partial sum. Use s of n. The first term is where we put 1 in here. So now the first term I'm going to use that. If we put 1 in for k, we have 1/2 minus 1, right? Sorry, the other way around. This should be negative. This will be negative. 1 over k minus 1 over k plus 1. One over 1 minus 1 over 2. Sorry. When we write that out, I saw that immediately. This is negative. So, sorry. 1 over k minus 1 over k plus 1. 1 over k is bigger than 1 over k plus 1. So it should be like this. Right. The next one, put 2 in for k, 1/2. Minus 1/3. And then put 3 in for k, 1/3 minus 1/4. And all the way to put n in for k, 1 over n minus 1 over n plus 1. So those an, a1, a2, a3, a sub n. Now, we have 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 over 1 over n minus 1 over n plus 1. So what we have here is called a telescoping series. That cancel out. This cancel out. And cancel out everything except the first and the last. Common denominator of n plus 1 n plus 1 minus 1 is n, and then we have n over n plus 1. Right, so that is the formula for the partial sum, and this kind of series is called a telescoping series. Meaning that something will cancel out, and essentially we just have the first and the last term. And if this goes to infinity, that will be the sum. Right. We'll see this a few more times. Should be number 3. Summaries. So we have a sequence and series. Over here we have functions. Right. Independent variable. Or index. A sequence and series, we use n. A function, we usually use x. The dependent variable. We have a sub n. And f of x, just different forms. Domain. Integers. and the function, the domain could be anything, not only real numbers, but could be complex or whatever. So just straight real numbers or subset of real numbers, to be precise. If we add them up, we have a series or a sum, and if we add them up, we have the integral. And then we have a finite or infinite series. So we have the sum that goes to n, or the integral go from 1 to n. However, when we say the accumulation over infinite interval, that is not indefinite integral. Right. The bottom line is a function we use f of x, and a sequence we have the term a sub n. It's just different notation. We don't use subscript in function. We use the parentheses, and we use subscript in the terms of a sequence. Right. With that, we go to the next section. Sequence. Change the title. By the way, I posted the review for test 2. It is a little bit long, longer than 3 hours. That is optional. Usually, when I ask you at the end of the class for the note, it is only for the lecture notes and not for the review. So, if you have a question on the review, just go to that and then fast forward to whatever the question is. I should put the timestamp, but I have a lot of other things to do, so I didn't have time to do the timestamp. Right. So in this section, what we do is we study a lot about sequence. In this section, in particular, the limit of the sequence. Suppose f is a function such that it is equal to a sequence a sub n for all positive integers. And we have the limit as x goes to infinity of f of x equal to L. Then the sequence, then the limit of the sequence a sub n is also L. Sorry. Right. So what it says is that a function is a sequence is a function. If the function go to a limit, then the sequence also go to that limit. So, but the fundamental difference between the sequence and a function is that a function defined on all real numbers, meaning it is defined on the continuous interval, whereas a sequence is defined on points that are not continuous. So a sequence is discrete and function is continuous. One is finite. I should not say finite. One is countable points and the other one is not. Right. But bottom line is the limit of the function is the same as the limit of the sequence, which means the significance of this is all the rules we have about the limit of the function will apply to a sequence as well. So this kind of get back to calculus 1 at the beginning, where we find the limit of a function, but this time we find the limit of the sequence. Similar way. Right. Sorry. Right. Don't get too hung up with the notation. Just again the curly bracket, we give a list of the numbers, which is a sequence, and the term is inside is n over n plus 1. So we just find the limit of this when n go to infinity. So when we say the limit of the sequence, it's always go to infinity, because the sequence by definition is an order list. So it order from the first to the second to the third and so on. So when we say the limit of a sequence, we mean at infinity. Right. So pretty much we'll find the limit as n go to infinity, and a sub n is equal to that. And we did this before, right? So as n goes to only the highest power matters. That's why we take the highest power on the top and the highest power terms at the bottom, n over n, which is 1, and limit of 1 is 1. So simple enough, right? Take the highest power on the top, divide by the highest power at the bottom. So it will be the same thing for the next example. So determine the limit of this sequence a sub n equal to 0 to infinity. It could be 8 n equal to 1 or 0, it doesn't matter. What matters is it goes to infinity. I will change the problem slightly. Right. Not slightly, I think completely different. Instead of that problem over there in the note, I'll change into this instead. Right, so we'll find the limit of the sequence, meaning goes to infinity. So, same things apply. We have power of n or power of x. Only the one with the highest power matters. So we check pretty much that. Square root of n is n to the 1/2. So let me write this again. 3n cubed take the highest power on the top and highest power at the bottom. And then simplify. We have 3 over n, right? N cubed and n cubed cancel out to have 3 over n. Now when we put infinity in for n, when we have a finite number, divide by infinity, could be plus or minus infinity, doesn't matter, that goes to 0. So the sequence has the limit of 0. Always say the sequence converges to 0. C theorem. Right, so this will come in handy. By this I mean, for that one, finite divided by infinity is 0. And if we have polynomials or power of n or power of x, as the variable goes to infinity, only the highest power term matters. Right. Now, this is properties of the limit. The same thing as the properties of the limit of function. assume that a sub n, the sequence a sub n and b sub n have limits a and b respectively. Then the limit of a sum or a difference is a sum or a difference of the limits. For constant multipliers, we can take it outside, and then for a product, and when I write a quotient as 5 still a over b as long as b is not equal to 0. And now when we have a product, is the product. So this is kind of straightforward. But the limit of a sum is the sum of the limits, limit of difference, or products, or quotient. Still, I will be difference, sum, and different quotient or product of a sequence. Yeah. Limit of a sum is the sum of the limits, usually. That's how we say it. So it's no big deal here. So the note is over there. Two. So since we talk a lot about limit and important things about limit, sometimes we have to use the L'Hopital rule. And now this next part is just the review of section 7.6. This will come in handy a lot in this chapter. L'Hopital rule and indeterminate forms. In particular, for this form 1 to infinity, 0 to infinity, and infinity to 0, those forms. So assume we have that, and this one have one of those forms. Of that, what we do is first we'll let y equal to it, and we'll evaluate pretty much will check ln on both sides. And check the power down. Finally, is that. Next, the growth rate. Now we just review section 7.6. Now, if we know this, this section will be a lot easier if we know that. So, suppose I think we should have a lot more example than what we have in the note. Right. Suppose we have two functions, both of them goes to infinity. But both of them go to infinity. They may go to infinity at different rates. So that's what we define here. Right. When we say f grows faster than g, we write f grows faster to infinity if if we go faster to infinity, either we have f of x over g of x is equal to 0, or if we flip it, could be negative infinity, positive infinity. Right. Once again, if the ratio is equal to infinity, the top is bigger. If it is equal to 0, the bottom is bigger. If it is infinity, the top is bigger. If it is equal to 0, the bottom is bigger. And if it is anywhere in between, have comparable rate, comparable if the ratio is a constant. So this section, usually when we say the limit equal to something, we mean that number is finite. And that number is less than infinity but greater than 0. So just write like that. So it's not 0, it's not infinity. Right, theorem. Right. And this will come in handy if we can use this effectively. That is not number 9, that is Q. X to the X. Right. And for this limit, what do we have is P, Q, R, S are positive. Are positive, meaning that greater than 0 and B greater than 1. Right. Let's take 5-minute break here, and when we come back, we find the limit of some of those functions. This will be the last one, the more difficult one. Right, continue at 10:08. Right, we continue. First example. The first one has nothing to do with this. By the way, we will get back to this. But when we write ln to the q x, we mean ln of x to the q power. We can let q equal to 1 if we choose to. As long as it is bigger than 0, it's fine. Right. The first one, we're not using anything here. We just use the L'Hopital rule. There's no x in here. So we're trying to find the limit of this sequence. Yeah, just inside the bracket. Right. So if we put infinity and infinity in here, let's just do that quickly. That doesn't help much, right? But infinity plus 5. So kind of cancel out. So this one, we have the form of indeterminate of 1 to infinity. Right. So to do that, what we do is we're going to let y equal to it. So let y equal to that limit. And then we'll take ln on both sides. And we did this quite a few times. The reason we take ln on both sides, so we can take the power n down. By the way, when we write like this, I can also split it and write like this. Right. And that's 5 over n and n over n. So 5 over n, why don't we write 5 times n to the negative 1? And n over n cancel out is 1. So we can write like that. Now, by default, we can say n to the first power. Now, the reason when we write like that, remember, if it is indeterminate form, we use the Hospital rules. In order to use the Hospital rule, we need a ratio of two functions. So we check n to the first to the bottom becomes that. So we need to have a ratio for the Hospital rule. So we use the Hospital rule. Derivative of the top over derivative of the bottom. Derivative of ln derivative of ln is 1 over the parentheses and then times the parentheses prime. Derivative of the bottom is negative n to negative 2. Right, so I have 5 n to negative 1 plus 1. Derivative of this is negative 5 n to the negative 2. At the bottom we have negative n to the negative 2. Cancel those out. Even the negative and the negative cancel out as well. Cancel that out as well. So we just have 5. That cancel completely. We just have 1 over 5n to negative 1 plus 1 times 5. I'm going to put 5 on the top instead. And the bottom, n to negative 1 move to the bottom. Right, and then next we have 5 over n. Now as n goes to infinity, finite divided by infinity is equal to 0. So that one goes to 0. We just have 5. This one goes to 0. So we end up with 5 over 1, which is 5. Right, this is a typical problem where we take ln on both sides. You will see this a few more times. And finally, that is not the limit. We have ln of y is equal to 5. To get rid of the ln, we raise both sides to the exponent. And a and ln cancel out. So y is equal to a to the 5th power, and that a is the limit of the sequence. Right. So, like I said, you should see this a few more times. where we use the Hospital rule and we have to take the ln on both sides. Right. Next. Right. We have that sequence. So how do we find the limit of that sequence? Right. If it has negative power, move to the bottom. Right. Of course, we can use the Hospital rule, but this time we use everything we have from the previous section, the growth rate and everything. So we use this part here. Right. So let me write this out because this is very important, and I want you to use this instead of jump right into the limit from the beginning. Let me write that out. What is very important. Right. So remember, we have ln of x to the qt So we have that order. Then see how does that help, right? Let me just write down everything first. In that case, P, Q, R, S are positive, and B is bigger than 1. So P, Q, R, S bigger than 0, and B bigger than 1. When we have those, we have this order. By the way, when you take the test, I recommend that you have this somewhere so you can reference to quickly. Right. Now, and then we're matching. What is n to the 10 power? Which one of this? By the way, n is equivalent to x. So, in that case, where is n to the 10 power? N is equivalent to x, right? So x raised to some power. So right here we can put the n to the 10 power is here, where 10 is p, right? As long as p is positive. So n to the 10 power is equivalent to that. And then e to the n power. So n is the variable equivalent to x, and e is the base, is a constant. So b to the x is equivalent to e to the n. So we say that the bottom is significantly bigger than the top. So in that case, what is this limit equal to? Now think about this. If the bottom goes too fast to infinity compared to the top, It has to be equal to 0, right? If the bottom goes too fast to infinity, then this limit equal to what? Right. So if the bottom goes faster to infinity, the whole thing goes to 0. If the top goes faster to infinity, it's go to 1. I think we should have a lot more examples than these two. Right. Now I'm just going to ask you to find the limit at n goes to infinity of ln of n over square root of n. So square root of n, we can write that as n to the 1/2. And ln of n is just ln of n. Right. Now, like I said, write that somewhere where you can reference to quickly. Right, so ln of n, by the way, as mentioned before, this is equivalent to ln of x to the q power. Now, so which one's which? So first of all, the ln of n is going to be this one. N equivalent to x, and q, in this case, let q equal to 1. We have ln of n. So ln is going to be that. So what is n to the 1/2? Well, n is equivalent to x to the 1/2. So n to the 1/2 is here. So which one? Again, the bottom is bigger than the top, so this one equal to 0. So we have the bottom goes to infinity faster. So this equal to 0. Like I said, we need a lot more example. How about we find the limit of 2 to the n over n square. So, which one of those on what list? Right, 2 to the n, the variable on the top So 2 to the n is this, where b is equal to 2. And then n squared is here. So the top is bigger than the bottom. So we say the top goes to infinity faster. If the top goes to infinity faster, then the whole thing will go to infinity. So right. So if the infinity on the top, if it goes to infinity faster, on the top, the whole thing goes to infinity. If the bottom goes to infinity faster, it goes to 0. Right, try one more. Right. We cannot really put in anything on this list. However, we can write like this. (1.5) to infinity. I just keep getting bigger and bigger to n. And we have 1.5 to infinity. Of course, it's infinity. By the way, it might be that list. Of course, we have to write in general like that. But a similar version of this is ln of n is less than, growth significantly slower than n to the p. Just going to drop that. Right. You might refer to a simplified version of that. Of course, this includes everything. This is a little bit less, but certainly we can use. So for this one, let me note that p is the power that is bigger than 0. Could be 0.001, but b have to be bigger than 1. Right. On the test, this will be good enough. Of course, the general version is that. Again, if the top is bigger, let's just say it. If the top goes to infinity faster, then the ratio will go to infinity. If the bottom goes to infinity faster, then the ratio go to 0. Right. So that's the simplified version of this. We will get back to this a lot more later, but for now, of course, the whole list is that. So yeah, like I said, the test, this should be enough. 3. Some terminologies. Yeah. Right. All the terminologies over there, I'm just going to write it down. It is increasing if the next term is bigger than the previous one. Now it is decreasing if the next term is less than the previous term. Sorry, I should copy that directly from the note. But anyway, if you have this, just ignore the note. This is the same thing. Non-decreasing. I write it down without reading the note. Right. Non-decreasing meaning that it is increasing or flat, not increasing. And then non-increasing is non-increasing meaning that it could be decreasing or at least it have to be equal to. Right. Monotonic. Monotonic is either non-increasing or non-decreasing. So either one of this. So bounded above. If there's an upper limit. It's bounded above if there is a number that is bigger than all the terms. And again, I've write it out without reading the note. Is bounded below if it is bounded below if all the term is bigger than or equal to L or N. And it is bounded if it is either bounded above or bounded below. 8. Right. So that are the terminologies of sequence. Increasing or decreasing is easy, but we will see a lot more those two, non-increasing and non-decreasing. Non-increasing is could be decreasing or could be flat. So for example, we might have something like 1, 2, 3, 3, 4, 5, 5, 6, 7, and so on. For example, we might have something like this. It is increasing except it equal for those two numbers. So in this case, we call this one non-decreasing because that is not decreasing. Right, just the way we call it. B example. Determine if the sequence are bounded. If yes, find the limit. Find the bound. Right. Look at the first example. Right. So when we look at this, 1 minus 1 over n. Right. Now, think about this. As n increases, what this one goes to? Right, let's just write out a few terms to see what happened. When n equal to 1, that's a terrible way to write it. This is better. Right? 1 minus 1 is 0. 1 minus 1 half is 1 half. 1 minus 1 third is 2 thirds. 1 minus 1 fourth is 3 fourths. If this pattern continue, looks like we go to n. N equal to 1, n equal to 2, n equal to 3, n equal to 4. Looks like we go to n minus 1 over n. which goes to 1. By the way, so we just write like this. 1 minus 1 over n is the same as n common denominator, right? And this one goes to 1. So actually this one is bounded above and bounded below as well. But so this one gets closer and closer to 1. So we say 1 minus 1 over n less than or equal to 1. So 1 is the bound. By the way, then we say if it's less than or equal to 1, then obviously it's also less than or equal to 2, right? If it's less than 1, then it's less than 2, obviously. So 2 is also a bound. But the sequence is bounded. One of the bound is 1. 2. One plus 1 over n we can certainly rewrite this common denominator now. Of course, when we take n goes to infinity, this one goes to 1 as well. So this sequence go to 1. But in this case, is that 1 is the upper bound or the lower bound? Think about this. Let's write out the sequence. One plus 1 over 1. 1 plus 1 over 2. 1 plus 1 over 3. 1 plus 1 over 4. And so on. So we have 2, 3 halves, 4 thirds, 5 fourths. If this continue, this will go to 1 as well. So both of them have the bound is both of the sequence go to 1. However, this one is less than or equal to 1, and the 1 plus 1 over n is greater than or equal to 1. So 1 is bounded above and 1 is bounded below. Right. This example is not really significant. I'm going to skip that. The only difference here is the negative 1 to the n power. And when we have that, we're alternating from positive and negative. Right. Like I said, that example is not really important. Go to number 4. More theorems. A. Geometric sequence. Right. Let R be a real number. Then R to the n equal to 0 if or absolute values of R less than 1 and equal to 1 if R equal to 1 and does not exist if absolute values of R bigger than 1. So let me do this. So absolute values is bigger than 1. When we write like this, we mean R is between 1 and negative 1. So when we have R to the n power, the limit will be does not exist on the outside. And 0 in the inside. And equal to 1. When it equal to 1 and will be does not exist if it equal to negative 1. So anything in between negative 1 and 1 it go to 0. Anything on the outside does not exist. At 1 is 1 and negative 1 does not exist. So that is R to the n power. And then also if R is positive, by the way, I'm not saying 0 is between negative 1 and 1. I'm saying when R is between negative 1 and 1, the whole thing equal to 0. When R greater than 0, then R to the n power converges. Or diverges. But most importantly is monotonically. Sorry, run out of space. So when it's greater than 0, monotonically. If R is negative, it is oscillation. Could be converges. Or diverges by oscillation. Oscillation, how do you spell that? Oscillation. Right, just think about this. When we have numbers like that, the sign will change from positive to negative, which is oscillation. If we have that, it's always positive. So that is monotonically. So positive is monotonically convergent or divergent, and negative it is oscillation, positive and negative. So when we have the oscillation, we might have the oscillation like this, in which case there's no limit. If we have the other way around, the oscillation like this, there is a limit, right? So oscillation meaning it just changing from positive to negative, and if it's just getting bigger and bigger, this one is divergent. If we have the other way around, still oscillation, but convergent. So that's why we have these scenarios. Right. So just keep that for now. B. Example 1. Find the limits. By the way, this is geometric sequence and not geometric series. That's different things. Again, sequence is a term by term. Series is the sum of the terms. What if we have the term equal to 2 to the 3/2 to the n power? Right, so what is the limit of a sub n as n go to infinity? So the limit, obviously we can take the constant outside. This is infinity. Now, so we have something raised to the n power. So what will be the limit? Let me go back to the theorem to make sense. Let R be the real number, then as n goes to infinity. Like that. Oh, better yet, just say, sorry. This is a lot better than. Please add the limit there so it makes sense. Otherwise, if n does not go to infinity, then r to the n is equal to r to the n, obviously. But we're talking about the limit as n go to infinity here. Right. Now, for this one, what is r equal to? R equal to 3/2 in this case, right? So if it is greater than 3/2, it's over here, it will be divergent. Because absolute values of r is bigger than 1. And it is divergent monotonically. Because it is positive. So we say a sub n is divergent monotonically. 2. B sub n equal to negative 1/3 to the n. So what's r equal to? negative 1 over 3, right? So in that case, what do we know about the sequence? If it's between negative 1 and 1, so it is convergent. But it's less than 0, so it will be convergent. Oscillation. Difficult to put that in adverbs, so we just say by oscillation. Oscillation. Once again, it is convergent because absolute values is less than 1, and oscillation because R is less than 0. So simple enough, right? Between negative 1 and 1, convergent. Outside, divergent. At 1 is equal to 1. By the way, in that case, if it is equal to 1, it is also convergent. Negative 1, divergent. Anything positive is monotonically, and anything is negative is oscillation. So that is geometric sequence. Right. So we have 2 over 3 to the n power. Right. So this is where we change a little bit, and we can say, how about 2 times 1 over 3 to the n power. Right. And 1, why don't we say by default 1 is 1 to the n power, and bring both of them under n. Now we have r to the n power. So in this particular case, r is 1/3. And then we can say the sequence, because that is between negative 1 and 1, it is convergent. And because it is positive, it is convergent monotonically, meaning that the sign will not change, and oscillation changing from positive to negative. Right. It is convergent because absolute values is less than 1. It is monotonically because r is positive. Right. We run out of time, so I have to stop here. Do you have any question before I end the stream? Once again, the test will be available by this Wednesday. After class on Wednesday, the test will be from 8.4 to 10.4. Right. Once again, do you have any question before I end the stream? Right. Other than that, I will end the stream here. And as always, thank you for watching, and have a nice day.